By now you have a good idea of what heat exchangers are and how they work. And you know some of the kinds of things that can go wrong with heat exchangers. In this unit, we're going to find out what to do to cure these problems. We'll also take a look at what's done to keep heat exchangers in the plant working efficiently. We'll be seeing routine maintenance, typical repair jobs, and online temporary fixes. What we're going to be doing in this segment is give an overview of the subject so you'll have a broad picture of what your job on heat exchangers is going to be. We'll also look into a couple of very simple procedures in more detail before going on to a close look at major tasks. Now, when a heat exchanger is out of service for routine scheduled maintenance, the first thing needed is a thorough cleaning. With surface heat exchangers, condensers, and other shell and tube units, this usually means cleaning out the water boxes or headers and clearing the tubes of any blockage. Cleaning and inspection is also done with direct contact heat exchangers. With direct contact heat exchangers, you're usually looking for corrosion and scale and some of the problems they'll cause. This might be blockage of inlet nozzles, or loose scale might get into clean feed water as it leaves the heat exchanger. Maintenance on direct contact heaters is usually nothing but rewelding or replacing trays and tray supports. Since this is about all you'll ever need to worry about with direct contact heat exchangers, we'll limit our discussion in this unit to maintenance of surface heat exchangers. Cleaning out condensers often involves scraping tube sheets and raking accumulated crud out of water boxes. Headers in large shell and tube units are usually cleaner. In smaller units, it's just a matter of disassembling them for cleaning. Your cleaning methods will depend on what's going through the heat exchanger and the kinds of impurities in the fluids. Cleaning the inside of tubes can be done several ways. On bigger units, if the buildup is moderate and easy to remove, such as slime from algae and other water growth, a stream of water under high pressure will do the trick. You use a water gun, which is just held in the end of each tube. Pulling the trigger shoots water through the tube. Now, sometimes compressed air is mixed with the water to churn the muck and sludge off the walls of the tubes. Now, if deposits are really hard to remove, the same gun is used to shoot the tubes with rubber plugs, wire brushes, or metal scrapers, sometimes called bullets. The one you choose depends on what you're trying to get out, and that depends on what's going through the heat exchanger. Another way of cleaning tubes is rodding. It's the elbow grease version of shooting tubes and is practical on small heat exchangers like a small oil cooler. And there are also devices like plumber's snakes used to clean drains and sewers. They remove the toughest stuff with a rotating scraper on a flexible cable. In large heat exchangers, tube bundles can be pulled out so the outside of tubes can be cleaned. Corrosion, scale, and deposits can be brushed off with wire brushes. Once the heat exchanger is cleaned out, a thorough and careful inspection is in order to find any leaks that exist. While the system was running, there may have been no evidence of leakage problems. Regardless, it's really important to make your inspection as thorough as possible. The more careful you make your inspection, the less likely it is that a problem will crop up before the next scheduled maintenance. A number of things go into this detailed inspection. To check for leaks in a surface heat exchanger, you may use a dye check or you may perform a vacuum test. Now, these might be done while the component is in service, or they might be performed while the unit's down after it's been cleaned. After cleaning, a visual inspection is done for evidence of corrosion, cracking, or to look for any more blockage. While some heat exchangers are in service, a telltale dye can be added to the water going into them to look for any leaks. This is usually a fluorescent dye that glows when it's exposed to black light, a source of ultraviolet light. Any leakage will show up where the dye comes through. On condensers and other heat exchangers which are run under a vacuum check can be used to look for leaks. It involves placing sheets of thin plastic wrap on the tube sheets to cover both ends of the tubes. This is done while a vacuum is drawn on the shell of the component. Now, the plastic wrap is just like the stuff that you use in your kitchen, and it sticks to the tube sheets as well as to itself. Now, if there's a leak in a tube, the plastic wrap will be sucked into that tube. That's a dead giveaway. After a condenser or shell and tube heat exchanger is clean and a good thorough inspection's been made, any leaks that have been found need to be taken care of. Now, generally, you plug a leaking tube at each end to keep fluid from going through. Normally, you don't try to stop the leak itself. Later on, we'll be seeing in detail how plugging is done. Sometimes you may find a leak around where a tube goes through the tube sheet. You might have to plug the tube, or you may be able to weld the end of the tube to the tube sheet. It's possible you may have to do both. Tube replacement is often a job that's farmed out. It may be farmed out to a refitter or back to the manufacturer of the unit. Sometimes, though, you may do such a job in-house. Tube replacement is almost always done in wholesale lots, when so many tubes have been plugged that the efficiency of the heat exchanger is affected. Tubes are usually set into tube sheets in one of two ways. One method is by rolling, which is a way of expanding the ends of the tubes into corrugated openings in the tube sheet. The other method is to weld the tubes into the tube sheet openings. Whichever way the tubes are set into the tube sheet, any that have to be replaced must be cut away very carefully. After removing the old tube, the new tube is set into place and fixed to the tube sheet the same way as the original tube. We'll be studying these things in more detail further on. We'll be going into inspection, cleaning, and repair jobs on both large and small heat exchangers. And we'll take a look at some of the equipment you'll be using on the job to see how it's done. Before we go on, let me mention the importance of sacrificial anodes. They aren't used in all heat exchangers, but attention has to be paid to them where they are used. There really isn't much you can say about sacrificial anodes, except that they're a little bit heavy. And the details of their maintenance are so simple that we won't spend a lot of time on the subject. We've already talked about them and discussed the way they work. They're called sacrificial because they are eaten away by corrosion rather than the metals of the heat exchanger. When they're worn down so far, they have to be replaced. Just when is usually a matter of judgment. But one rule of thumb is to replace them when they're more than 50% eaten away, or when they are in danger of coming loose from their mountings. Replacement is a straightforward job of just bolting a new one in the place of the old one, and you're done. After all the rest of your maintenance tasks are completed, it's time to clean up tools and equipment. When you've made sure that nothing's been overlooked, the unit can be closed up. It might be tested before it's put back into service. This might include flow testing, pressure or vacuum testing, leak tests, and so forth. It has to pass any tests that are performed before the component is ready to go back online. Routine maintenance tasks are usually pretty simple, about as simple as heat exchangers themselves. Still, each job has to be done with care and thoroughly completed. Then you can expect everything to work just fine when the system is put back into service. Now, before we go on further, pause to study the first section of your text and answer the questions. Get your instructor to clear up any questions you may have. When we come back, we're going to see what any big heat exchanger job begins with. So far, we've seen that heat exchangers are really pretty simple devices. It doesn't exactly take the skill of a surgeon to operate on a heat exchanger. And the tools you need to work on a heat exchanger aren't as varied and complex as those you'd find in the operating room either. Nevertheless, it's important to give thought and care to any job you do. The things you do to prepare for the job call for thought about what you'll be doing, and the precautions necessary to ensure doing the job safely deserve consideration too. Now, when we prepare for any maintenance job, we've got to select the tools necessary to do the job. These tools include safety items as well as stuff for mechanical work. Part of our preparations also include procedures we have to follow to ready the equipment to be worked on. These practices include shutting down the system and tagging equipment so it won't be operated while you're doing work. Now, when a work order comes down for a maintenance job, the first thing to do is check out the equipment you'll be working on. You should also look at any manufacturer's manuals or spec sheets on the equipment. This way you can figure out exactly what you'll need to do the job. If you know what you'll be working on, and if you know what the task is, then you can decide what tools and equipment you need. Let's see what this takes. Mel here just got a work order to open and inspect the water boxes of the main condenser on turbine unit number 12. Now, maintenance practices vary from place to place. In Mel's plant, the operations people are responsible for shutting down the associated systems and draining the condenser. In some plants, Mel might do this part of the preparation himself. Equipment tags are placed on all valves and controls to be sure they're not operated. This will prevent unpleasant surprises while the job's going on. While he's at it, Mel checks the size of the hardware so he'll have the right-sized wrenches to open the condenser up. Back at the tool room, it's just a matter of checking out the right tools and equipment and making sure that nothing's overlooked. And while we're at it, how about looking over the equipment to make sure it's okay? A visual inspection of tools and equipment can save a trip back to the tool room, or possibly might save a trip to the doctor. Let's take a look at the equipment needs for this job. Since Mel or his co-worker will be working in a wet, confined area, he chooses special low-voltage safety lighting to protect against a shock hazard. They'll need an impact wrench and a large socket to loosen the retaining nuts on the water box doors. And it would be a good idea to take a crowbar along just in case the swivel studs are really tight. A rain suit and boots will help keep them dry inside the water box, especially if they have to do any cleaning of the water box or the tubes. Now, if any chemical corrosion inhibitors were used in this system, very special precautions would be needed to protect the eyes and the skin. Many of these are chromate solutions, and they're especially hazardous if you have no protection. Sometimes breathing protection is even needed where these chemicals are used. They'll need an air quality check. A sniff tester, like this one, not only tells if there's enough oxygen to breathe inside the confined workspace, but also signals if there are any explosive gases present. In Mel's plant, the instrumentation people are responsible for doing this check, but in a lot of places, Mel would do it for himself. Now, since the cooling water in this plant's condensers comes in from the river nearby, there's likely to be a lot of muck inside. So in order to do a thorough and complete inspection in the condenser, Mel's helper is going to need to clean accumulated junk out of the water box and off the face of the tube sheets first. For this, he'll need picks and scrapers, and a rake will make it easier to get the big stuff. A shovel and a container to pass the crud out to be dumped round out what they'll need for this part of the job. Because they're sure of having to clean out the tubes, they'll be certain to check out a high-pressure water gun and maybe a bunch of scrapers, brushes, or squeegees to shoot the tubes with. This will come later in this job. And now it's down to the job. When our worker was looking over the unit earlier, he made sure the water boxes were drained and that equipment had been tagged out, so he knows it's safe to open up the condenser. It's been a while since this unit's been opened up, so the impact wrench will make it a lot easier to open it than if they had to use hand tools. The large nuts are backed off only enough to allow the studs to be swiveled out of the way. With the last one loose, the door comes open easily. After opening 2 doors on each side of the water box, the very first thing to do is an air quality check. This is necessary before you go to work in any kind of confined area. The sniff tester is calibrated for both readings it'll take. After calibrating the meter, a sample of the atmosphere in the water box is drawn into the tester through the nozzle at the end of the hose. The meter shows how much oxygen content is in the air and any percentage of explosive gases. If either reading falls outside the safe limits, an alarm goes off and the meter will tell you exactly what's wrong. In this case, there's plenty of oxygen inside and no gases are present to cause danger. If there were, the water box would have to be ventilated, or, if it were impossible to ventilate, anyone working inside would have to use a respirator. Even though the air inside the water box is safe, this crew has decided to provide ventilation using this large fan. The fresh plant air will make it more pleasant to work inside the water box. Now, this unit's been shut down for a couple of days, so it's cool enough to work in without danger of fatigue or heat exhaustion. If it were still hot, they might have to take special precautions, such as extra ventilation for cooling, or even reduce the work cycle to prevent heat exhaustion from working in a hot environment. Of course, our mechanics are observing the 2-man rule, too. This is a very basic safety rule for any kind of work in a confined space. There's always one man on the outside, not only to serve as a helper, but to ensure the safety of the worker inside. The man can call for help and provide assistance if the worker inside gets into any trouble. All these preparations and precautions we've talked about in this part of the program make the job easier and safer. Easier because the thoughtful planning that goes into getting ready for the job keeps the number of steps involved down to a minimum. And safer because the care that's taken to observe precautions in doing the job ensure that the worker doesn't have to deal with unnecessary dangers on the job. In this part, we've looked at preparations such as draining the condenser and shutting off valves and pumps in the system, choosing tools and equipment for the job, and opening up the unit. We've also talked about safety precautions like tagging out equipment, special safety lighting, air testing, and the two-man rule for working in a confined space. And we've seen all these preparations and precautions followed properly up to the point where the condenser is open and they're ready for work to begin. Now, all these procedures also apply to work on large shell and tube heat exchangers. In some cases, the headers will be opened up so the problem of a confined workspace doesn't exist, but gases can still be present as the head is coming off. We'll be looking inside a large shell and tube heat exchanger further on as we follow Mel's job too. Before we go on to the actual work to be done, pause now to read through Chapter 2 in your text and answer the questions. Your instructor will discuss any special procedures that are followed in your plant and can answer any questions you may have. When we get back, we'll follow our workers through their job cleaning and inspecting the condenser, and we'll also take a look at some of the same kinds of operations on large shell and tube heat exchangers. As we saw earlier, there are basically just two things that can go wrong with heat exchangers. One of these is blockage, and leakage is the other. In this part of the program, we'll take a look at the first one of these maintenance problems, blockage. We'll examine the problem in two ways. First, we'll talk about the various routines you'll be using to clean large surface heat exchangers. And second, we'll see some automatic methods of cleaning that are used to slow down a buildup of the things that stop up a heat exchanger. Now, depending on what fluids go through a particular heat exchanger, it's pretty easy to know just what to expect when you open up a unit after a long period of service. When our mechanic got the work order to open and inspect the main condenser on number 12, he knew pretty much what he was going to find. He planned the job accordingly. He chose the necessary cleaning tools as well as his personal protective gear. Once the unit was opened up and the air quality check told him the air was safe inside, all it took was a quick inspection to confirm his judgment. What a mess. Oh well, it could have been a lot worse. The unit had been in service for quite a while, and in all that time, this was all that had accumulated inside. Well, the first thing to do is suit up and go inside. Our worker's got to be careful of his footing in that water box. The surfaces in there are very slippery, and the last thing he wants to do is fall and take a bath in that stuff, or hurt himself. Scraping the tube sheet and picking things out of the ends of the tubes just requires patience to get it all. It really doesn't matter whether he cleans the tube sheets first or shovels out the water box. It's all got to go. But if the stuff in the water box isn't downright hazardous, it's more practical to clean the tube sheets first. Why clean the water box twice? Cleaning the tube sheets is made easier with the use of wire picks to get to the inside of the tubes with the most junk stuck into them. Be sure to use care, though. Some tubes are made of soft metal, and you could damage them. Bristle or wire brushes may be used later to get any slime accumulation from the face of the tube sheet. Once the tube sheet's been picked clean, our workers make a sort of two-man bucket brigade, passing all the crud out and dumping it for disposal. Shooting the tubes involves the use of a high-pressure water gun like this one. Depending on the kind and amount of garbage that's blocking the tubes, the mechanic may do the job one of four ways. If there's only mud or silt accumulated inside the tubes, he may just use a stream of water from the gun. Sometimes a gun like this may have a fitting that allows pumping in compressed air to churn stubborn accumulation off the walls of the tubes. A second method he might use is rubber squeegees that just fit inside the tubes. These are forced through the tubes by the stream of water. They remove slime or soft deposits from the tube walls better than water or water and air do. The third thing used to shoot tubes is a tight-fitting wire brush with rubber plugs at both ends. The rubber plug pushes the brush through on the stream of water from the gun. The plug that goes through first clears any soft deposits, while the brush removes harder deposits and scale. The fourth item he could use is for really heavy hard deposits on strong tube materials, such as stainless steel. This bullet is a finned scraper, which will scrape loose chemicals and corrosion deposits even wire brushes won't remove. In this case, the worker is using brushes to shoot the tubes. He inserts a bunch of them at one time into a section of tubes. He may do several hundred at once. When they're all placed in the tubes, he shoots them through one at a time with the same high-pressure water gun he uses when just shooting the tubes with water. It's really important to make sure no one's in the other water box. The force of the brushes coming through could hurt someone pretty bad. After he's done with one group of tubes, a helper will collect the bullets from the water box at the other end. While he's doing this, our mechanic places another bunch of bullets into the next group of tubes and signals his helper when he's ready to shoot them. Communications with everyone are really important, so no one will get hurt. To shoot the tubes, all he has to do once the bullets are in place is to hold the nozzle of the water gun firmly in the mouth of each tube and pull the trigger. He can feel the water pressure, and he can tell by this feel when the bullet has gone through and out the other end of the tube. Now, occasionally, the worker is going to find that a tube is blocked so badly that a bullet won't clear it. When this happens, he's going to get wet. This is why he's kept his rain suit on and why he's wearing safety glasses while he's performing this chore. Chemicals in the deposits or in the water could be harmful. In order to get all the tubes in the condenser or any big shell and tube heat exchanger, it'll take a fair amount of time to go through this process over and over again, a bunch at a time. Now, the basic job's not much different on a large shell and tube heat exchanger. In the case of this large heater, shooting the tubes was done with high-pressure water and compressed air, and that was good enough to remove the small amounts of scale that were in the tubing. Although the tools and implements are pretty much the same as the ones we saw the mechanic using on the condenser, one thing you have to think about with a U-tube heat exchanger is what you shoot the tubes with. Longer bullets or brushes can get hung up in the bend in the tubes. When the outsides of the tubes need to be cleaned, it's necessary to pull the tube bundle out of the heater. This flange is separated, and tracks and slides or rollers are provided inside the shell to allow the tube bundle to be pulled out. When the tubes are out in the open, you can wire brush scale away. In oil heaters, if you have to get all the oil off the tubes for any reason, you can use solvents made for that purpose. Now, once all the tubes are cleared, and when water boxes or headers are clean, the next job at hand is finding and plugging leakage. Before we follow on to the next step, though, we'd like to take a look at a couple of other ways of keeping shell and tube heat exchangers clean. One mechanical method some plants use is sort of like the snake a plumber uses to clean out your home plumbing. A rotating set of blades on the end of a cable is fed through the tubes in a heat exchanger to remove very tough, scaly deposits. Like the scrapers used in shooting tubes, this method of cleaning is usually reserved for the toughest cleaning jobs on tubes of strong material. In addition to these do-it-yourself methods, there are some automatic systems for keeping condensers and shell and tube heat exchangers clean. Now, these automatic systems fall into two categories. The first is mechanical cleaning, and the second is chemical cleaning. Automatic mechanical cleaning systems are found in many plants that utilize river or ocean water for cooling water in condensers and other heat exchangers. A common system circulates rough sponge balls through the tubes and collects them to be pumped back through. The use of these automatic systems cuts down on the need for periodic cleaning where fresh, clean water can't be used in a heat exchanger. Chemical cleaning systems automatically chlorinate the incoming cooling water to kill and prevent algae growth. The collection of slime on the inside of tubes and on tube sheets is reduced, and this keeps cleaning jobs to a minimum. Altogether, the methods we've examined in this part of the program, manual and automatic, are typical of the cleaning methods used in the plant. These methods are the methods used for larger shell and tube heat exchangers and for surface condensers. A little later in the program, we'll examine smaller shell and tube heat exchanger maintenance, but before we do, we'll look at maintenance practices to plug leaks in larger heat exchangers. For the time being, pause and read section 3 of your text and answer the questions. Your instructor will discuss the methods used in your plant to keep larger surface heat exchangers clean. Make sure you have a good understanding of these methods and ask your instructor to clear up any questions you may have. In the last section of our program, we talked about how there are basically only two maintenance problems with heat exchangers. Now, blockage was one of these problems, and we looked at the procedures you'll use to clear out blockage in large components. We also talked about cleaning out the heat exchangers before inspecting them for any evidence of leakage. Leakage is the second of the two problems you'll have to deal with when you work on heat exchangers, and that's what we're going to be talking about in this segment. We're going to follow Mel and his crew as they look for some evidence of leakage in the condenser we saw them cleaning. We'll also take a look inside the big feed water heater we've seen. We'll show you how leaks are taken care of in these big components too. Earlier on, we saw Mel and his helper clean out the condenser water box. They scraped the tube sheets and picked debris out of the ends of the tubes. Then the water box was shoveled clean. Finally, Mel's helper shot the tubes of the condenser to clear them of any crud that had accumulated inside them. Now that the water side of the condenser's been cleaned, they can look for tube leaks, and you can do this in a couple of different ways. One of these methods is a very simple test. This test uses the same plastic wrap that's so popular for use in the kitchen. Of course, there are many brands of this wrap available, but this is the stuff that seems to stick to everything, even itself. A vacuum is drawn on the shell side of the condenser as if it were in operation. Now, this step is unnecessary if the condenser is operating under reduced load with it half opened up. The plastic wrap is laid over wetted tube sheets like wallpaper. Sheets of plastic are overlapped so all the ends of the tubes are covered. You do this at both ends of the tubes so they'll be sealed off completely. If there's a leak in any tube, the plastic wrap will be sucked into the ends of the tube that's leaking. You can even tell how bad the leak is. If it's big, the wrap may be sucked in so hard it'll pop in the opening. Other substances can be used for this test. A soap and water mix or foam can be brushed over the tube sheet. Where the bubbles are sucked in reveals leaking tubes. Wherever a leak is found, the tube is plugged at both ends so the cooling water won't get into the condensate when the system's running. Tubes are plugged like this instead of being repaired because it isn't possible to get into the tube bundle to all the places a tube might be leaking. In a minute, we'll see how leaking tubes are plugged. But before we do, let's look at another way we have to look for tube leaks. This is a test that has to be done when the turbine is shut down. Now, this way is more involved, but it allows you to find leaks you might not be able to detect with the vacuum test. Our second method uses a fluorescent dye to seek a leaking tube, and here's how it's done. After the water side of the condenser has been drained and cleaned, jacks or supports are placed under pads on the condenser. This is because the shell of the condenser is going to be flooded with water. The jacks and supports are necessary to hold all the extra weight on the shell. Remember that many main steam condensers are suspended below the turbine and they just won't hold up under all the water's extra weight. Once the supports have been put into place, the operators flood the condenser with clean water with the fluorescent dye added. As the dye mixes with the water, any leakage from the shell into the tubes or around tube ends will become visible under black light. Black light is the light produced by an ultraviolet lamp. It causes the dye to glow bright green. Wherever there's dye coming out from around a tube end or out of a leaking tube, it'll be easily visible using this method of inspection. So we've seen a couple of common methods of locating leaking condenser tubes. Other methods may be used, but generally any method used will be a variation of the two we've seen. Be sure to learn how it's done in your plant. Once the leaking tubes are found, they get plugged to keep cooling water from contaminating the condensate in the shell. Now, tubes can be plugged in one of several ways. Remember that to do the job right, you have to plug the tube at both ends to keep the cooling water out. There are several kinds of plugs for this purpose. What kind of plug to use may be chosen by the component's manufacturer, or your plant may have special requirements. Your instructor can fill you in on how to find out in your plant. The most common are made of a fibrous material and are shaped like the stopper of a bottle. They're tapered so you can fit them into the tube ends and then just hammer them in tight. They'll stay in place partly because water pressure will push in on them. Also, the fibrous material of the plug will tend to expand when it's soaked with water to hold the plug in even more tightly. Other kinds of plugs are used to do the job too. Some of the older plugs used in this condenser have slotted heads. They're threaded plugs that screw into the ends of the tubes. They cut their own threads, sort of like a wood or sheet metal screw. The threads grab into the metal of the tube and hold tight. These are metal plugs, and they don't have to expand in place to hold tight. Now, long experience has shown that the heat and vibration that's present when the unit's running doesn't necessarily loosen plugs too easily, so metal tapered plugs can be hammered in tightly enough to hold. A metal tapered plug will sometimes seal a minor leak between the tube and the tube sheet by forcing the end of the tube more tightly into the hole in the tube sheet. To be sure it's sealed, if there's any doubt, a metal plug can then be welded around to make a permanent, positive seal. Another type of plug that's sometimes used to seal a leaking tube is an expandable plug. These have a rubber donut sandwiched between two large washers with a bolt running through the middle. When the bolt is tightened, the rubber is forced to expand outward. This seals the tube tightly enough that the plug won't loosen and come out. For extreme service requirements, such as high-pressure heaters in nuclear power plants, there are even explosive plugs that are detonated to expand them into place. Now let's take a look at plugging leaks in a high-pressure feedwater heater. Here we'll see two other methods of plugging tubes and leaks between tube ends and tube sheets. This big heater has been opened because it was known that it had some leakage. When they opened it up, they found that some tubes were leaking, and they also found that some of the tube ends had vibrated loose from the tube sheet and were allowing leakage. Two different kinds of plugs were used in this heater. The older ones are expandable metal plugs. The hard metal pin in the middle is driven in with a hammer and forces the softer metal of the plug to expand in the tube end. The others are tapered metal plugs just installed recently. Notice that some of these have been welded in place. They've done this to seal a leak between the tube end and the tube sheet. Where several adjacent tubes may have come loose at once, the whole bunch of them is welded over to seal any further leakage. If the tubes were much larger in diameter, they might have welded plugs in the ends of them. Now, whether we're talking about a condenser or any other shell and tube heat exchanger, there's only a certain percentage that can be plugged before the heat exchanger begins to lose efficiency. Usually you can plug between 10 and 20% before it affects the component's efficiency. You can find out what that percentage is on the piece you're working on by checking manufacturer's spec sheets for that component. For this reason, and also to make sure that plugs haven't come out during operation, it's important to record exactly which tubes are plugged. When you know that you're reaching the maximum percentage, you can plan tube replacement well in advance. When that maximum percentage is exceeded, it's time to replace the tubes. When that's done, usually all the tubes are done at once because it's most economical to do it that way. Usually, tube replacement is a job that's contracted out to a refitter or to the component's manufacturer. This may involve having to ship pieces out, or the component may be repaired at your facility. Depends on the size of the component. Tubes are replaced by carefully cutting them away from the tube sheet so the tube sheet isn't damaged. New tubes are installed the same way the old ones were put in, and this could be one of two ways. Rolling tubes is the first way. It's a method of expanding the ends of the tubes into corrugated holes in the tube sheets. The corrugations hold the tube in place and provide a strong seal against leakage. The second way tubes may be fixed to tube sheets is by welding. And this is usually done for components operating under high temperature and high pressure conditions. Welding is done carefully and provides a very strong bond between tubes and tube sheets of compatible metals. In either case, it'll probably be your job to prepare the heat exchanger for the retubing job. And this will mean you'll have to rig the component to open it and close up the component after the tube bundle is back in place. This will involve the careful rigging of the parts of the heat exchanger. Gaskets to seal large header plates and gaskets to seal large baffle flanges may have to be cut from big sheets of gasket material. The sealing surfaces will have to be cleaned smooth of all old gasket material which may be stuck to it. With everything placed carefully, it's a mighty job to handle the impact wrenches. These huge wrenches have to be rigged themselves, they're so heavy. It takes 2 people to do this task, to get these nuts tightened on the studs. After everything's back together, a pressure drop test will be used to make sure the unit is really tight. Now, this is a test where one side of the heater is pressurized and the other is left open. When the pressure source is closed off, any drop in pressure shows evidence of a leak. All these procedures we've seen in this segment, inspection to find leaks and the ways you have to seal leaks, are part of the procedures you'll probably follow from time to time when you're called on to do maintenance on large heat exchangers. In a moment, we'll go on to look at maintenance on smaller heat exchangers. Before we do, read the 4th chapter of your text and work the exercise. Your instructor can tell you what work is done to detect and plug leaks in the large heat exchangers in your plant. Any special information on the units you'll be working with can be found in manufacturers' spec sheets and manuals. So far in this program, we've seen many routine maintenance tasks you'll be performing on large heat exchangers. Condensers and big shell and tube heat exchangers are all dealt with in pretty much the same way. Now, small heat exchangers, such as this lube oil cooler, have the same kinds of maintenance problems, blockage and leakage, but you'll handle them differently. For the most part, heat exchangers used in the plant fall into 2 extremes. The larger ones we've examined up till now are fixed in position and maintained in place. Smaller ones, on the other hand, can be brought into the shop for their maintenance. They're portable enough for you to pick them up and handle them. What we're going to do in this part of the program is look at a typical maintenance routine on this small cooler. Specific things like where the inlets and the outlets are and the configuration of the headers may vary among different units. But the things we'll be seeing are basic to most all the small shell and tube heat exchangers you'll be working on. These mechanics have already removed the lube oil cooler from the motor pump assembly it was serving. Since the system had to be put back in service immediately, they replaced it with a unit that had previously been rebuilt. They pressure checked this one to see if there were any leaks before they rebuilt it. What they'll do now is open this one, clean it out thoroughly, replace gaskets and seals, and test it. Then they'll put it back into stock until another one like it needs service. The first step is to drain the cooler thoroughly. When they've gotten as much out as possible, the front header is loosened so the seal can be broken. This way, the rest of the oil and water can be drained from the tubes in the shell. Once both fluids have been drained from the cooler, the guys can finish taking it apart without spreading the mess too much. First, he removes the front header. This is the header he had loosened to finish draining the unit. With the header off, it's pretty easy to see why they're having to work on this cooler. All that buildup comes from the cooling water flowing through the tube side. The water is unpurified river water, and the accumulation of silt and slime is a lot like some of the junk that collects in a condenser. Next, off comes the header at the other end. Notice the rotation cycle of loosening the bolts until they are free from tension on the shell and header. This is to prevent any possibility of warping the header or the shell. Once each header is removed, the hardware is set carefully aside so it doesn't get lost. The mechanic now has access to both ends of the tube bundle, and both tube sheets can be scraped clean. He's doing this step of cleaning with a putty knife, using care not to gouge the tubes on the tube sheet. He's not likely to cause any harm, but it is possible to do damage that might cause leaks. When the tube sheets are scraped, he wipes them clean with a rag. Now he's ready to rod out the tubes. The rod has an end which fits snugly inside the tubes, and as it's pushed through each one, drives all the accumulated sludge out of the other open end. It doesn't make any difference what direction the tubes are rodded in. Both ends are the same, and they're both open. After rodding each tube, the mechanic wipes off any remaining sludge from the tube sheets. Cleaning the gasket surfaces at each end of the shell comes next. Using a scraper, the flat surfaces have to be cleaned to bare metal. They can't leave any old gasket material stuck to the mating surfaces that would keep them from sealing tightly. Once the last little bit is removed, the shell and tube bundle can be set aside, and it's time to work on the headers. Our mechanic needs a putty knife to dig out the sludge from inside the headers. He gouges out the last little bit before he scrapes the gasket area clean. He's got to be just as thorough as when he cleaned the gasket mating surfaces on the shell. Every bit of old gasket has got to go. The surfaces have to be smooth, bare metal in order to get a good seal. He goes through the same routine to clean the other header. First, he gets all the accumulation out of the inside. Then he scrapes the gasket surfaces clean so the seal will be good when the cooler goes back together. When all this is done, he makes a final close inspection of all the parts to make sure he hasn't overlooked anything. He's also looking for any damage that might be apparent. If any were found, it would have to be corrected before he reassembles the component. Now it's time to lay out all the materials and hardware to put the cooler back together again. When he reassembles the cooler, he carefully checks the fit of each gasket. Then he uses a light, complete coating of gasket cement on the mating surface of the shell. This will hold the gasket in place so it will stay perfectly aligned when the header is put on. Gasket cement also helps provide a more perfect seal, so he smooths the coating on the other mating surface too. Then it's back on with the header, carefully making sure everything lines up just so. While he holds the header in place with one hand, he threads the nuts onto the studs carefully and runs them down by hand until they are finger tight. One by one, each nut is threaded onto the studs until they are all snug. When all the nuts are tightened down in this manner, he takes a hand wrench to tighten them the rest of the way. In order to make sure the header is tightened down uniformly, he tightens the nuts in a crisscross pattern. This assures that the parts will not warp and that the gaskets will provide a tight seal. Now, some heat exchangers, like this one, may require the nuts to be tightened with a torque wrench. Whenever you're working on a piece of equipment, a check of the manufacturer's manual or maintenance bulletin will tell you torquing requirements. It'll give you any other special information you need to know, too. On this particular cooler, the manufacturer doesn't specify the torque required to tighten the nuts, so the mechanic uses careful judgment to tighten the nuts uniformly. He's also careful to avoid twisting that wrench too hard. He doesn't want to take a chance on stripping the threads on the studs. After the other header's back on, when everything's uptight, a final external cleaning with a rag is just plain good practice. The last step before they put the cooler back in the storeroom for the next time it'll be needed is to check and make sure there are no leaks. And one way to do this is to hook up the tube side inlet to the usual cooling water system and then plugging the outlet. Now, when the valve is open to allow water to flow, there should be no evidence of leakage either at the gaskets or into the shell from the tube bundle. Another way of checking for leaks is a little cleaner, since you don't have to use cooling water to look for leaks. All you do is plug the outlet as before, but the inlet is connected to a source of compressed air with a gauge between the valve and the cooler. The valve is opened and the shell is pressurized. You've got to be careful here not to use too much pressure, or you could cause a lot of damage to the cooler. Then the valve is closed, and you watch the gauge to see if there's any drop in the pressure in the shell. If not, you can figure the component is leak tight. These are the same types of tests they might have used before they took the cooler apart. After it passes the leakage test, it's ready to go back on the shelf for future use. If any leaks are found, usually it's easier to replace the tube bundle with a new or rebuilt one. Later on, the tube bundle can be rebuilt and put back for future service. From what we've seen in this unit, maintenance on shell and tube heat exchangers is pretty basic once you have an understanding of how they work and how they're made. You'll only be looking for ways to fix two heat exchanger maintenance problems: blockage and leakage. And the way you'll be dealing with these problems will depend on the physical size of the component as well as the circumstances of its use. None of it is all that difficult, but just like any mechanical job, it needs your attention to doing the job right to avoid problems later on. When you've completed the exercises on heat exchangers, you'll be ready to tackle any of these jobs in your plant.